Molecular geometry, molecular polarity, nonpolar molecules. In this tutorial, we will be going over molecular shape and polarity, revisiting dipole moments, nonpolar molecules with nonpolar bonds, nonpolar molecules with polar bonds, and some examples at the end. Molecular shape and polarity. Whether or not a molecule is polar or nonpolar depends on two things. The first is the type of bond, the distribution of electrons within an individual covalent bond. Nonpolar covalent bonds always result in nonpolar molecules. Polar covalent bonds may result in polar or nonpolar molecules depending on the molecular shape and distribution of the electrons throughout the molecule. Distribution of electrons. Molecules can either be classified as having a symmetrical or an asymmetrical distribution of charge. In other words, electrons. Bond polarity arrows drawn above each individual polar covalent bond present in a Lewis structure for the molecule can be used to determine whether the molecule is polar or nonpolar. Bonding dipole moments can be displayed as polarity arrows with an arrow pointing from the less electronegative element to the more electronegative element. The geometry of the molecule contributes to whether all the individual bond polarities, in other words, the bond polarity arrows, cancel or not. This is represented by a net dipole. Revisiting the concept of a dipole moment. Recall that a dipole moment is a measure of the separation of positive and negative charge in a molecule. The greater the difference in electronegativity in a bond, the greater the bonding dipole moment. So polar covalent bonds will have large dipole moments. Nonpolar covalent bonds will have smaller to zero dipole moments. So in this model of diatomic oxygen, there is a zero dipole moment because both of these polarity arrows cancel each other out. They're pointing in opposite directions because the electronegativity difference here between the two oxygen atoms is zero. In water, we have a large dipole moment because if we take the difference between 3.4 and 2.2, we get something greater than 0.4. Because remember, from 0 to 0.4 is the relative area for electronegativity differences talking about a nonpolar bond. You'll also notice that we have this net dipole here, which is basically saying, hey, all of these shared electrons plus the lone pairs are pulling towards oxygen, giving it that slightly negative charge and the hydrogen slightly positive charges. So as soon as we see that, we know we have a dipole, two poles, and therefore a polar molecule. Since diatomic molecules are linear molecules composed of two atoms from the same element, there is no electronegativity difference in the resulting nonpolar covalent bond. As we can see in all of these models below, they all have the same electronegativity values. Each atom making up the nonpolar covalent bond exerts an equal coulombic attractive force on the bonding electrons shared between the two atoms. These coulombic attractive forces cancel out since a diatomic molecule has a linear molecular geometry. Thus, diatomic molecules have no net molecular dipole and are nonpolar molecules. Nonpolar covalent bonds have a zero dipole moment. Nonpolar molecules composed of polar covalent bonds. These molecules contain polar covalent bonds. However, the geometry of the molecule results in an overall symmetric charge distribution in the whole molecule. In other words, no net molecular dipole. When the central atom is surrounded by identical terminal, in other words, surrounding atoms in a symmetrical manner, all of the individual bond polarities, the bond polarity arrows, cancel and the molecule is nonpolar. This pattern will be observed for all the major classes of molecular geometries: linear, trigonoplanar, tetrahedral, trigonal bipyramidal, and octahedral. Let's look at our first example, linear, Xenon difluoride, Xef2. In this Lewis structure, we can see the polarity arrows showing 0 net dipole as they're pointing toward the more electronegative fluorine atom. The 3 lone pairs surrounding that Xe are on a different plane and push the fluorine atoms as far away from each other as possible, giving a bond angle of 180 degrees. Because these polarity arrows cancel each other out, the molecule is nonpolar. Trigonal planar, Boron Trifluoride Bf3. This Lewis structure representation would lead us to the conclusion that boron trifluoride is a polar molecule due to the individual bond polarity arrows not all canceling. Because you could look at these 2 bond polarity arrows and be like, oh yeah, those are totally canceling each other out, but oh no, what about this one? This molecule must be polar. Well, not so much. But this Lewis structure representation more accurately reflects the trigonal planar molecular geometry with the 120 degree bond angles. The individual bond polarity arrows will all cancel, leading to the conclusion that boron trifluoride is a nonpolar molecule. Additionally, boron, the central atom, this B right here, is surrounded by identical terminal atoms, the 3 fluorine atoms, in a symmetrical manner. So the shared electron pairs between the boron and the fluorine are all pulling equally out towards the fluorine. Therefore, this would be considered a nonpolar molecule. Tetrahedral, carbon tetrachloride, CCl4. We can see here again that the terminal atoms are all chlorine, so there's equal pull in all directions as the polarity arrows point from the less electronegative carbon to the more electronegative chlorine. The arrows cancel each other out, showing no net dipole. Therefore, this is considered a nonpolar molecule. Trigonal bipyramidal. Our next example is phosphorus pentachloride, PCl5. In this one, you really need to be careful because, again, all the terminal atoms are the same. They're all chlorine. And we look at these polarity arrows and we can see that this arrow and this arrow cancel each other out because they're on the same plane. And then these 3 arrows, here, here, and here, represented by these chlorines in this 3-dimensional model, also all cancel each other out. Very similar to that trigonal planar representation. So because all the arrows cancel each other out, there is no net dipole in this molecule, and it is considered nonpolar. Octahedral, sulfur hexafluoride, SF6. Here, same thing. We really need to pay attention. We can see that the terminal atoms surrounding the sulfur are all exactly the same. The fluorines are oriented, so they're opposite of each other. They are pulling in opposite directions, and every polarity arrow has another polarity arrow canceling it out. There is no net dipole on this molecule. Therefore, it is considered nonpolar. Square planar, xenon tetrafluoride, Xef4. Again, even though we do have these 2 lone pairs, one here and one here, they are on a different plane. So these fluorines, as we see in this 3-dimensional representation, are all opposite of each other. The polarity arrows will cancel each other out, and there is no net dipole in this molecule. Therefore, it is a nonpolar molecule. So what did you learn in this tutorial? We went over the idea of molecular shape and polarity. We revisited the idea of dipole moments. We talked about nonpolar molecules with nonpolar bonds, then nonpolar molecules with polar bonds, and then looked at a bunch of different examples. Need more help? Feel free to contact me. Have a great day.